In this mini lecture, we are going to solve 3 different example problems that all treat a moving charge. In these 3 problems, we are given different initial starting conditions, and we're asked to solve for different quantities. But again, in all 3 of these problems, we are going to have to use the ideas of work, potential energy, or the change in potential energy, and electric potential, or the change in electric potential. For problem A, we are moving a charge from a potential of 134 volts to a potential of 305 volts, and that takes us 2.4 times 10 to the minus 3 joules of work. What is the value of this charge? Well, to solve for this, we can start with our equation that work is equal to minus the change in our electric potential energy. And we also saw earlier that the electric potential energy is the same as the charge times the change in the potential difference. So work then is going to be minus Q times our change in potential difference. If we solve this equation for Q, Q will be equal to minus our work divided by the change in potential. So minus our work. This change in potential is your final potential, so that will be V sub B, minus your initial potential, V sub A. And this will be minus 2.4 times 10 to the minus 4 joules divided by V sub B, 305 volts, minus V sub A, 134 volts. And that gives us a charge of minus 1.4 times 10 to the minus 5 coulombs. All right, so how did we get coulombs? Well, remember that 1 volt is a joule per coulomb. So we'll have a joule on top. We've got this joule here. So we've essentially got 1 over an inverse coulomb, which you take 1 over an inverse coulomb, you'd get back a unit of coulomb. Our charge in this problem is going to be minus 1.4 times 10 to the minus 5 coulombs. In problem B, we have an electron, and this electron has been accelerated from rest, so my initial velocity here is A. Now you're going to have to pay attention to, am I using a velocity or am I using a potential? And I don't always do a super great job of making my V's different or smaller or larger to represent which one's a speed and which one is a potential. So that's something you will have to figure out how to do when you're solving the problems and to keep those straight in your brain. So my electron has been accelerated from rest, so our initial speed is 0, through a potential difference of 66 volts. What is the kinetic energy in electron volts? Since we know the problem is asking us for a kinetic energy, that's a really great hint that we want to start with conservation of energy in order to solve this problem. So, conservation of energy. Our initial kinetic energy plus our initial electric potential energy equals our final kinetic energy plus our final electric potential energy. If we start from rest, our initial kinetic energy is 0. So it's this final kinetic energy that we're going to be solving for. Now, what I'm going to do, actually, I'm going to subtract my kinetic energy over to the left side, okay? Minus KEB. So I'm going to have minus KE sub B, that's my final kinetic energy, equals my final potential energy, and I'm going to subtract now my initial potential energy to the other side, minus our initial potential energy. So I subtracted my final kinetic energy over to this side, and I guess I skipped writing that step here, but I'm going to subtract my initial potential energy to the other side. So then I'm left with this equation, minus my final kinetic energy is equal to my final potential energy minus my initial potential energy. And this is our final minus initial. That's our change in potential energy. Minus our final kinetic energy is equal to this change in electric potential energy. We can write the change in potential energy as Q times the change in the potential, or the potential difference. That's equal to minus our kinetic energy, final kinetic energy. I'm solving for the kinetic energy. Well, I've got this minus sign here. I'm going to multiply both sides of this equation by -1. So I have positive my final kinetic energy here equals minus Q delta V. Okay, so this kinetic energy is equal to minus my charge on an electron is minus 1.6 times 10 to the minus 19 coulombs. And then I have to multiply it by my potential difference, which was 66 volts. Okay, so then I take minus times a negative, that becomes a positive. So this quantity is actually positive. 1.6 times 10 to the minus 19 times 66, and that gives us a kinetic energy, a final kinetic energy of 1.056 times 10 to the minus 17 joules. But we wanted our answer in electron volts, not joules. Now, 1 electron volt is the energy given to a fundamental charge to accelerate it through a potential difference of 1 volt. 1 electron volt is 1.6 times 10 to the minus 19 joules. So I'm going to use a conversion factor to convert this from joules to electron volts. 1.056 times 10 to the minus 19 or minus 17 joules times, we've got our conversion factor in 1 electron volt, there is 1.6 times 10 to the minus 19 joules. So we're taking this number essentially and dividing it by 1.6 times 10 to the minus 19 joules. Joules cancel, and that gives me a kinetic energy of 66 electron volts. The moral of the story for this problem then is that if we are taking a fundamental charge, 1 electron, and we're accelerating it from rest through some potential difference of n number of volts, the kinetic energy of that fundamental charge is then that number n of electron volts. Because remember, the definition for an electron volt is the energy given to our fundamental charge to accelerate it through a potential difference of 1 volt. So if you're accelerating your fundamental charge through a potential difference of 66 volts, then the kinetic energy required to do that is 66 electron volts. For problem C, we have an electron, which I'll remind me of that by denoting it here with E minus. Our electron is accelerated from rest, an initial velocity of 0 meters per second, to a final speed, which I'll call V sub b, of 1.75 times 10 to the 7 meters per second. Through what potential difference, here I'll call that delta V, did our electron travel? All right, now here's a really great example of a problem where we've got 2 or 3 different quantities all kind of represented by a V. So you're going to have to remind yourselves of which V is which. This delta V here is for my potential difference. These V's right here are for my speeds of my particle. Now, in order to solve this problem, I'm also going to think about the conservation of energy. So we'll have our initial kinetic energy plus our initial electric potential energy equals our final kinetic energy plus our final electric potential energy. Now, we start from rest, so our initial kinetic energy is 0. Okay. I'm going to move this kinetic energy term to the left. I'm going to move this potential energy term to the right. We'll have minus my final kinetic energy is equal to my final electric potential energy minus my initial electric potential energy. Now this right here, our final potential energy minus our initial potential energy, that's our change in potential energy. And our change in potential energy is also Q times the change in the potential, or Q times my potential difference, okay? And my kinetic energy here, I'm going to write this as minus, we've got the minus sign there, 1/2 mv squared. And that's our final velocity squared. So we have minus 1/2 mv squared is equal to Q times the change in my potential. I'm trying to solve for the change in the potential. I was given V here, and since I have an electron, I know the mass of the electron. I'm going to go ahead and solve this equation for the change in the potential, or the potential difference. So delta V is equal to, I'm going to say, minus 1/2 mvb squared all over Q equals minus 1/2. Now the mass of an electron is 9.1 times 10 to the minus 31 kilograms. Our speed, our final speed of this electron was 1.75 times 10 to the 7 meters per second. We've got to square this. And then we're dividing it by, we've got an electron, so the charge on my electron is minus 1.6 times 10 to the minus 19 coulombs. All right. We plug all of this into our calculator. We get that our change in potential, or our potential difference through which this electron travels, is 871 joules per coulomb, which is the same thing as a volt. How did we get the joules per coulomb, or the volts essentially? Well, we've got a kilogram times meter squared over second squared on the top. Kilogram times meter squared over second squared is already a joule, and then we're dividing it by the coulomb. So that gives us our joule per coulomb, which we also refer to as a volt.